everybody. Welcome to my talk, Crossing the Barrier Between Kotlin and Rust, and back. There's so much Kotlin multi-platform this past day and a half that I debated renaming this talk to Rust multi-platform, but fortunately didn't get a chance to do that. Welcome to my talk. Who am I? My name is Tarik. I'm an engineer at Mozilla. We're at Mozilla. I've been writing Rust with Kotlin for about 3 years now. I've been writing Rust with a few other languages as well, but a lot of what we do is writing Rust and exposing it to Kotlin, to call it into Rust. I work on Firefox Sync. So Firefox Sync is the end-to-end encrypted system that gets your data from your phone to your computer, for example, and back, without anybody at Mozilla, myself included, ever taking a look at it. Sync is one of the main reasons I'm doing this talk. Sync itself has a lot of client logic, a lot of logic that handles what happens when you add a bookmark on one device and you delete the folder that holds that bookmark on another device. All that logic is written in Rust, and it's exposed to Firefox for Android, Firefox for iOS, and Firefox for desktop. And in Firefox for Android, we call into it using Kotlin. And we do an interesting work there, where we have a lot of tools that help us do that, that we're going to talk about today. I'm Tarik, Eshaq, everywhere you can find me. Do feel free to reach out. And a quick thing about the slides, they're published online. I'll have a link to them at the end, so you don't need to take a photo of any slide or anything like that. Awesome, so here's what we're going to talk about today. We're going to start with why you would ever do this, call Rust from Kotlin or the other way around. Then we're going to talk about what it means to actually cross the barrier between Kotlin and Rust. And we're going to describe the fundamental problem we're trying to solve here, and then we're going to move on to how we actually do it at Mozilla. At the end, we're going to talk about the how a decent bit. It's going to be hopefully the majority of the talk, and we're going to talk about the tools that we've built. Some of those tools are some of the most exciting things that I've ever worked on, so I'm excited to share those with you today. Fundamentally, it's 3 questions: the why, what, and how. And I would have succeeded in this talk if y'all can come out being able to answer those questions. All right, so let's start with the first one. So why would you ever use Kotlin with Rust? Well, really, you probably shouldn't. Unless you're building a browser, for example, or something like that, you probably shouldn't. Crossing the barrier between any languages really adds a lot of complexity. Developer experience starts to become something you have to deal with quite heavily. You have to figure out how to have Rust developers that know Kotlin, or Kotlin developers that know Rust, and that's easier said than done. And among other tooling issues that come along the way. But I wouldn't be standing in front of you here today if there wasn't a time to do this. So here are a few cases where maybe you would want to do this. So first, maybe there's an existing Rust library. More and more over the past few years, we've seen foundational libraries getting written in Rust, some of them getting rewritten in Rust. That's a whole other topic. And some of them conveniently expose Kotlin APIs for you that you might even be using them without even knowing. Some don't, and that's where maybe your team might consider using some of the stuff we're talking about today to cross that barrier into Rust. The other thing is maybe you'd like granular memory management. You probably don't. Like, really, you probably don't. But maybe you actually work in a situation where you'd like granular memory management. In which case, Rust is a great option. It's becoming more and more of a great option. 10, 15 years ago, you would have used C and C++. Now Rust is presenting itself as an alternative. More and more of the industry is moving towards it. And I have some links all the way at the end for some resources that are the slides, if you're more interested into why people are moving towards this. Maybe the overhead of a runtime or garbage collector is too expensive. Again, it probably isn't, right? Depending what you're building, it probably isn't, especially if you already have Kotlin running on the JVM or something, or even Kotlin multi-platform. There's already a runtime. So it's probably okay to write the rest of it in Kotlin. But in some cases, if you have a critical section of your code, some part that actually does need to run without a runtime, then Rust could be a good solution for that. The other thing is maybe you'd like to take advantage of Rust's first-class cross multi-platform support. Kotlin multi-platform, maybe. But kidding aside, this is one of the reasons why we picked Rust as well. One, we are building a browser, Firefox. Two, Rust is a first-class cross multi-platform support. It's a systems programming language. It can easily compile to any target you can think of, more or less. So this is really the why, and hopefully, if there's one thing you take out of this is, if you're building a regular Android app where you don't have the necessary performance requirements or the granular memory management requirements or any of that. Nowadays with Kotlin multi-platform or other solutions, you might have a better way to do this, but in some cases, Rust is the right option. So that's the why. Let's chat about the what. So what does it mean to cross the barrier between Kotlin and Rust? And in this section, we're going to go a little bit foundational. We're going to talk about things that maybe the last time you talked about them was in a systems class in school, maybe deal with them day to day. So we'll see how that goes. So first, we're going to talk about what it means to cross the barrier between a language and another. And then we're going to take it back into Kotlin. I'm going to take a small detour. We'll talk about something called the ABI. Does anyone know what ABI stands for? Just shout it out. Yes, so what person just said is application binary interface. And what it is really, and this is by no means a rigorous definition, it just helps me to explain what we're going to talk about. It's a contract that is enforced by machine code. If you're writing your own machine code, you're defining your ABI everywhere in your machine code. If you're writing your own assembly, typically you don't do that. A compiler takes your beautiful Kotlin code, your beautiful Rust code, and converts it into code that you hopefully never have to look at. That code is the machine code that gets generated is what has your ABI everywhere. Specifically, what I'm going to be talking about today in terms of ABI is it controls how data is laid out in memory. So you can have an assembly generated or whatever that understands how to read or write a piece of data into memory, your RAM, your virtual memory, or whatever, and how that memory is laid out is a part of what we'd call your ABI. It also controls calling conventions. So if you have a function calling another, how data is passed from one function to the other and control flow going back, that is a part of your ABI as well. We're going to take a look at a quick example. So what we see in front of you is a Rust struct. Structs in Rust are just a bunch of memory that is usually stored in memory together, or a bunch of things that are usually stored in memory together. And in this case, you can imagine you have a question, a part of a Q&A form, for example, and you have the content of the question, an ID, which is a U32, an unsigned 32-bit integer. This is not production level code, it's just an example. And then you have, for example, the author name for that question, and that's also a string. So what we're going to look at next is how maybe that gets laid out in memory. So again, maybe. Remember, those ABIs are just contracts. As long as they're enforced by the compiler, they're good. It may be laid out a completely different way. So you'd have, for example, 24 bytes for the string. If anyone's curious, strings in Rust are 24 bytes because there are 3 values, a pointer, and 2 numbers. And then you have 4 bytes for example, your 32-bit number. And then you have 4 bytes of padding. If anyone who remembers their systems courses or anybody who works with this on a daily basis knows that this is for alignment, but really performance. I think machines do well when they know how to read and write memory in easy ways. And then you have your 24 bytes per string, the other one. It doesn't have to be this way. That's really the core idea of the ABI is it's enforced by the compiler so that when a part of the machine code is writing this question, it writes it this way, and it reads it the exact same way. So the other part we talked about is calling conventions. So for example, you have a function here called add. Very simple. Takes in 2 signed 32-bit integers, returns the sum of those 2. And a bit of a content warning. We're going to look at some assembly. It's going to be very brief, I promise. It's going to be x86. It's going to be brief. It's easy to understand. So this is a bit of the assembly. One possible way that this function here could have gone compiled to. And this is just instructions. So the first one is a move instruction. It moves something from EDI to EAX. Does anyone know what EAX and EDI are? Just one word? Registers, right. Small pockets in your CPU. For small pockets of memory in your CPU. And the first thing is there's a first contract being exercised there, which is that your A value is in EDI. That's part of your ABI. right, is your machine code that got generated assumes that A is in EDI, and then the next instruction, it assumes, so it puts it in EAX, and then a second instruction assumes that the second argument B is in ESI, and adds it into EAX, and then it returns, and it's assuming that the consumer knows that the return value is in EAX. So when you call it, for example, by passing 4 and 3, on the left side is the new code. It's fairly simple. You're putting 4 into EDI, 3 into ESI, and calling it. What you're doing here is you're exercising a contract. This contract is enforced by the compiler as it's compiling your code. And if there's one thing to remember out of the what of this all, is that crossing the barrier between a language and another is really a problem. How do you create a shared API between languages where they got compiled using different compilers? Different compilers enforce all sorts of conventions throughout their machine code. How do you make them agree? How do you call something from Kotlin into Rust agreeing or accepting that Rust expects values in a specific way and making sure that you know how Rust expects them? It's C. It really all boils down to C. So C has been there for ages. At least convention boils down to C. C has been there for ages. Every single language nowadays needs to call into an operating system call. And in doing so, it needs to kind of talk C in order to do that. So by convention, every language already knows how to speak C or how to speak C's conventions. And thus, what we end up doing is we just tell languages, hey, you don't need to speak Rust or speak any language. You just need to speak C. And on the other side, you just need to know how to accept C. So what does that look like in practice with Kotlin and Rust? Start with your Kotlin. You call into C-compatible Kotlin, which calls into C-compatible Rust, which calls into actual Rust. You can also do it the other way around. There's nothing fundamentally preventing you from doing it the other way around. You need to find out where you start and where you end, but you can do it in either direction. Those things in the middle, one, they're very error-prone. Two, nobody really likes to write them. It's the kind of code that you write and you hope that nobody touches it ever again, because it escapes all of Rust's safety mechanisms. It escapes all of Kotlin's safety mechanisms. You're writing C. Nobody wants to do that nowadays. We call this the foreign function interface. In a way, it's how a language talks to the outside, so it's a foreign function interface. And what I like to call this, the whole thing, is the FFI sandwich. So you have your buns at the top and the bottom. You have your Kotlin and the Rust. And this is where you usually spend a lot of your time. And then you have the juicy bits in between that can make or break your application. So what it means to cross the barrier between Kotlin and Rust really means traversing the FFI sandwich. And you can generalize this as well. If you're calling from any language to another, you're typically traversing an FFI sandwich of some sort. So how do we do it at Mozilla, or how do you actually do this? One, you can handwrite that code, but like I just said, nobody really wants to. It's the kind of code that will lead to undefined behavior, a bug that you discover 5 years later when your users are having issues. So how do you do it at Mozilla? We started handwriting at first. Again, didn't work out. So we wrote a tool called Unify. And what Unify is, it's a multi-language binding generator for Rust. Bindings is really the code that calls, think of it as a part of your FFI. That C part of your FFI is another name for that. It has first-class support for the JVM Kotlin. So it will generate all of that C-like Rust code, but it also knows how to generate that C-like JVM code that knows how to call into that Rust code, so that you don't have to worry about it. There's community support for Kotlin multi-platform by outside contributors outside of Mozilla, and it's one thing we did with Unify is we made an open extension, and we've seen folks from the industry implement bindings for Go, C#, among other things, while we support or we maintain the Kotlin, Swift, and Python bindings. So the best pitch I have for Unify is that Unify generates the inside of the FFI sandwich, so you really only have to worry about the buns. So what used to look like this ends up really looking like this. It's still the same. It's not really different. It's just that it's hidden from you. Again, every problem can be solved with an extra layer of abstraction and all that. All right, so what we're going to do next is we're going to dig into a quick example of this, and we're going to show some features of Unify, and that's going to be the remaining of this talk, describing a bit of the how and why this was attractive to us at Mozilla. So we're going to introduce some quick, this is going to be the only slide that has only Rust and no Unify or anything in it. So this is just to help us understand what we're talking about. What we're going to have is a Q&A app. You can add questions, get questions, that sort of thing. This is just a type that exposes your API, your addition, all that. And then you'd have for example, a question that you want to add. This is the question we got from before that you want to add into your Q&A list. And this you can think of this as a data class where it has all the content, and then this one here could be your class in Kotlin, so to speak. Well, I guess there's another slide of just Rust, but this just shows us some of the functions you might want. You might want a constructor. You might want an ability to add questions into your list. And the Rust engineers in the room, if there are any, are like, why is this not mutable? Because you're adding a question. Not going to talk too much about that. I will a little bit. Short story. The way Unify works is it needs to enforce a certain type of guarantees across threads. So you can only have immutable references, and then you have to enforce mutability using mutexes and other ways if you want it. Anyway, so let's look at how Unify actually works. So one way to do it, when we have another way to define your interface outside of Rust code, so that is an option for people that want to do that. But one way we like to do it is you can annotate your function. So this here is a procedural macro in Rust. It's similar to annotations in Kotlin. It takes in your actual code, and then it generates code, takes in code, outputs code. And in this case, you're saying, for this Q&A manager, I want it to be an object, in other words, a class that can be called from the outside. You can call methods on it, and so to speak. And what Unify is doing here is it's taking this and it's generating that C-like layer. And it's also generating some metadata that can be used by Unify itself, again, at a later point to generate the Kotlin code, for example. And if you want to get your actual methods and functions to be exposed, you do a Unify export on the whole block where you're exporting some functions, and you annotate your constructor. This will make it when you generate your Kotlin code, it is an actual constructor, and then any public functions are by default exported because you're exporting this over here. So this looks cool and simple. So let's look at what calling into it from Kotlin looks like. But before that, actually, the question here again, we need to. Like we said earlier, it's not just about calling conventions, it's also about data layout. We also need to annotate this question itself so that when it's written out and in out of Unify, we know how to represent it. And we annotate as a record, data class. So let's look at some Kotlin. So for Kotlin, you construct it by, as if you're writing any Kotlin. You get a type QA manager, you construct it, that looks fine. And then you have your question. This is a regular data class. And when you do this is not going to even cross the FFI. Unify is smart enough to know it's a data class. When you pass it back, you're going to have to copy it. So it just creates the data class for you in Kotlin. And then when you add a question, you're calling it as if you're calling any other Kotlin function. Unify is even smart enough to try to convert conventions for you. Because if you look back here, add question moved into camel case. Which is the convention in Kotlin. So that's sweet, and this will cross the FFI. The constructor as well will cross the FFI. You don't even need to think about what's going on underneath. Part of my title is calling back into Kotlin, and we have support for that as well in Unify. And the way you do it is you have a trait. Traits in Rust are very similar to interfaces in Kotlin. They define behavior. And you define a trait, and then you export it, and you say with foreign. In other words, Rust should expect that other consumers from the outside could implement this interface with their own implementations and pass it in. So in this case, for example, HTTP client with one function that gets questions. And then you can have this Rust function that accepts this over here. For anyone that doesn't speak Rust, so to speak, this might look like, what the heck? Really, this is anything that implements that HTTP client and wrapped in an atomic reference count, but you don't have to worry about that for now. And then you can use it as if you're using regular Rust code. So from your view, it's anything that implements that Rust trait. You're writing regular Rust code, you call the get function, you get your result, and in here you're actually crossing back into Kotlin, doing any processing you'd like. For example, if you want to keep your networking in Kotlin land, you want to keep some threading in Kotlin land, you don't want to be giving away some type of control over something over to Rust. And then you can do whatever processing you'd like with that. In Kotlin, you implement it, the interface, just like any other interface. You're going to get a function, and then you just make sure that you implement it properly. And when you call into the your Rust code, you just pass in your implementation of that interface, and Rust just knows what to do with it and call back into it. You can also handle. Unify has ways to specify errors. For example, you can annotate an enum or anything really as a Unify error. Rust is one of those languages where there is no concept of exceptions. Errors are just regular types. It's just that there's conventions of how you deal with them. So you can annotate it, for example, this QA error as an error, and then when you return it as a part of this result type, then Rust knows that when it generates your Kotlin, there's a possible exception that will be thrown called QA error, and it has a few variants that you should try to handle. Another thing that Unify supports is async Rust. So async Rust is fairly new, and it's fairly new, and it works in its own model of async. And Unify supports it, and you can export. You can just export a regular async function, and Unify will do the right thing for the most part. So, and then when you call it from Kotlin, what gets generated is a suspend function. And you call it from Kotlin as if it's any other suspend function. You deal with it as if you're dealing with any other suspend function without knowing that you're actually calling into Rust, which is doing its own async thing. And the very cool thing about this is that the async, or what Rust is doing, or really Unify is doing in this case, is it's defining what it means for there to be a foreign executor for Rust's async system. So really it's Kotlin's runtime that's actually moving those async tasks forward, as opposed to there being an actual runtime running within Rust, which is really cool. And one of the last features we're going to talk about here before I show some very quick demo of some of this is calling async Kotlin from Rust. Same way that you can go forward, you can go backward. Again, there's nothing fundamental that's blocking us from doing it. And one way to do it is, or the way to do it is just have a regular trait. You export it the same way we did with our other trait. And anybody who's written any I/O code probably looked at my earlier examples like, what? You're calling a network request in a blocking function? Why? Well, you can actually have an async function to do your network requests. And you have an async function to do a network request. And in Kotlin, what you're implementing is an interface with suspend functions. So this is the same thing, except it's a suspend function, and you do with it however you may. And then within Rust, when you call, for example, a sync function to sync your data, you pass it again. You can pass it again this HTTP client, and it generates async Rust, or the trait has async Rust functions. So you call it as if you're calling any other async Rust. And when you do here, you're suspending the Kotlin task that's running this. And once the value comes back, you're continuing. And then again, the same thing here. When you await, you're actually suspending in the same Kotlin way of suspending, as opposed to a weird runtime that's running here. Awesome. So what we're going to do here is we're going to quickly show some actual code about what I just talked about. This is easier to understand, or this is just so that we understand how some of this code actually looks like. Can everybody see the code? Yeah? Sweet. OK, people at the back raised their hands. That's awesome. So what we're going to look at here is, again, this is our QA manager. This is some Rust code. And apologies for the lack of syntax highlighting. It's easier to just have one Android Studio thing as opposed to switching between IDEs. So you have QA, you have your Q&A manager here. Same thing here, exposed using a Unify object. You have your HTTP client trait. I wouldn't worry about the additional bits here. It's just regular Rust code. So anybody who's writing Rust would be able to understand what's going on here. And then you have your impl block. This is where your methods are, and you're exporting the whole thing. So you have your constructor. A slight difference to the slides I showed earlier. In this case, I'm actually taking in my HTTP client as an argument so that I can hold on to it and then invoke it whenever I'd like to. Means that the reference will stay with me in Rust until the whole QA manager is deallocated. But that's the nice thing of how we're doing it here is references are kind of handled nicely. In a way that the QA manager itself exposes a reference to the outside, as long as it's being held by Kotlin, this will not get collected in any way. We have our constructor, the same way we did. And then we have three functions here. We have a get that gets your local questions. You have a write that writes to your local questions. And you have a sync that will go and synchronize with the remote server. This is a nice pattern to have. Sometimes you want to run an application that works offline, and then when it goes online, you actually want to synchronize with the server somewhere. It's a really, really extremely simplified model of how sync works, but that's a nice way to work with it. Let's look at some Kotlin. And we're going to start all the way up with the imports here. And then, yeah. So really, we're importing three different types. You have your question record, which represents your questions themselves. You have your QA manager, which represents the API surface that you're going to use. And then you have your HTTP client, which is that interface that you're going to implement. And this is just plain Kotlin. So you're not writing any C code, anything that looks like C whatsoever. And then in here, for example, you're implementing this Kotlin HTTP client the same way you would any other HTTP client. Apologies for the lack of idiomatic Kotlin. This is mostly demo code. And then you have, so another function implemented in HTTP client. And then whenever you want to sync with a server, you're calling this manager .sync, syncs your data with the server. But otherwise, it will write your data into a local storage. So let's see this in practice, and hopefully this works out. Ta-da. Sweet. So this is pretty much it. So when we start right now, there is nothing. You can say, for example, how do I use Unify? You submit, and then it's fine. It's just writing to a local data store. There's nothing magical here. And then you sync with your server. Well, it looks fine. Nothing really happened. So what I'm going to do here is another cool thing about Rust, and Rust having first-class support for cross-platform things. It compiles very easily into WASM. So what I'm going to do here is I'm going to sync, and voila, I just got my how do I use Unify. Think, whoa, how did that happen? Really, it's using the same code. The same fundamental core, the same fundamental core bit of Rust. It is being used in my demo in my slides as is being used in my app. And I can answer that question. I can say Rust. I know this is Q&A, not really a place to write answers, but I'm going to do it anyways. You can submit. And then before I sync, and you can go back here, and you can verify that before I sync, it's not there yet. But of course, once I sync my data, I'm going to go back and sync the server. It shows up. Really, it's the same Rust code underneath, both in the Kotlin case and in the WASM, because WASM itself has a lot of support with Rust. I didn't have to write any C-like code. It's all just code and a little bit of JavaScript to call into it, and a little bit of Kotlin to call into this. And it just works. Sweet. So that's all I have for you today. There's definitely a lot of time for Q&A, so I'm happy to answer any questions you may have. And also, yeah, I'll keep this open as well. You can find the slides. If you scan that QR code, it'll take you to the slides. And any code I use in the demo is there. You can look at the code as well if you'd like to. Yeah, if you want to raise your hand high up so people can see that you want to ask questions. Sweet.
So the implementation for UniFFI implementation for Kotlin, does it use JVM FFI?
Yeah, so the one that we support, as in Mozilla supports has a first-class support for, yes, it uses the JVM, and it uses a library called JNA, which is Java Native Access, which is on top of JNI interfaces. Yeah, but there is also a community project that is Unify Kotlin multi-platform that supports all sorts of ways to interface with Rust from Kotlin.
Cool. And because in Java 22 there's now like the foreign function and memory interface, so like the new version of JNI, I guess. So I guess there will be support for that in the future.
Yeah, that's a good question. I'm not super familiar with the new version, what the implications of that are.
It's not LTS
but hey, that's a good question. You can ask it in for example, at the Unify GitHub issues, and we'll get to it. Yeah.
Hello. Hello.
Hello.
Great presentation. Thank you for that. So, if I understood that correctly, like you are interfacing in the way that you first build your Rust code and then you build a Kotlin, right? And like that is how it works, like from the dependency point of view and like from the functional point of view as well. Are you able to do it the other way around as well, so that like first like compile Kotlin and then use it from Rust? That's the first question. And the other, if you do you need to do any kind of annotation in the Kotlin code, or does it work out of the box, or?
Yeah, that is a great question. As far as I know today, no. So we don't have that support of you're launching something from Rust and then calling into a Kotlin library of some sort and back. In most of our use cases, at least internally, it's always been you're calling from Kotlin into Rust, and then sometimes you want to do something back. For example, HTTP client, and that's what we do at Mozilla, is our HTTP client, or our networking code, lives in Kotlin among other places, but it doesn't live with the Rust code that we're writing. So we have to call back into Kotlin, which figures out how we do our networking. So that's really been our use case for calling back. Fundamentally, there's, I imagine it to be possible. It's just not a problem that we've tried to tackle ourselves.
So, hello. So, I have two questions. So, the first one would be, how do you handle panics?
That's a great question. So, it's really up to you in a way, right? So, depends how you do your panicking in Rust. So, if you have it crash in Rust, then it will crash your process. And maybe that, and in a lot of cases, that is what we want, right? But in Firefox for Android, we don't do that. We actually unwind and return a special exception that, in a way, we're trying to tell the Kotlin consumer, hey, maybe you're going to record this into somewhere and then crash right away, please. But yeah, it's up to you, kind of. Yeah.
Yeah. So you don't. So it's up to the user to use catch unwind, or do you do that automatically in Unify?
Yeah, so we do it automatically in Unify. However, if for example you've set your Rust project to crash, like I think it's abort or something, then it should automatically crash. So catch unwind will do nothing.
All right, thank you. And to my second question, you expose the Rust struct basically as classes in Kotlin. How do you take care that after you instantiated and used your objects in Kotlin that the Rust structs are correctly deallocated? Yeah,
so we've made some changes very recently about this. I may not have the latest, but at first it used to be, so all of our, this is way back, all of our objects that would get exposed from Rust into Kotlin implemented auto-closable, so you need to kind of know to make sure you're calling them in the right way. I know we've made some changes. I think we maybe implement cleaner or something like that. I'm not a JVM expert, so I'm not exactly sure, but we've made some recent changes on that. But before, back then it used to be. Just as long as you call it the right way, we're going to deallocate it properly, but not anymore.
Yeah, thank you. That sounds like a garbage collector on top of a garbage collector.
I mean, not really, right? As long as you're just calling the right function at the end, then it's fine. If you're using auto-closable, then it's like closing a file, right? Which is the same thing. And there is no runtime, right? It's all just references in Rust and reference counting.
Hello? Hello? Here?
Hello? Oh,
Here,
there it is.
Yeah, nice talk. Yeah, thanks for that. How would you normally package this then? So you would generate your crate. Let's assume we are in production, right? So I have many crates. Now I want to annotate and generate the stuff. So what's the practice there? It's always over, Gradle. How would you do that?
Yeah, and that's a great question. I didn't talk too much about it today, but I can show a little bit of what that looks like in practice, because that's what we have here. Yes, so you'd use Gradle, and there's tools that we have for that. For example, we have a plugin. I'm going to show the name of it in a second here. So we have a plugin called, bigger, there it is. Yeah, so we have a plugin called Rust Android Gradle, and that does some of the magic bits of compiling the Rust code. And then there is the magic bits of actually generating your Kotlin code, and with that you'd run a script. Really, it's a Rust binary you can run against your crate, and then it will generate your Kotlin code. So I can show a very quick example of what that looks like over here. So in practice, that ends up looking something like this. I know there might be an actual like Gradle plugin for this. It's just while preparing this presentation, I just wanted to get something up and going. But yeah, this is like a binary you run against your shared object, which has all the metadata it needs. Yeah. Any other questions? 7 seconds in silence. Heard recently that's how long it takes introverts to ask questions. I don't know if it's been 7 seconds, but thank you all.